Alright, seriously, what is energy? Hello, welcome to the channel. Energy is undoubtedly one of the most commonly used and misused terms stolen by the public from physics. It is sometimes used to refer to how lively someone is, the lifespan of your mobile phone, or even to denote karma and other mystical and likely imaginary forces. My sense is that people believe energy to be something tangible, a kind of fluid that moves between us and surrounds us in an aura. In this, popularizers may have some blame. I'm sorry to disappoint you, but the reality is that the nature of energy is more abstract. Here's how it goes. Take any physical system and choose two different moments in time. Then, gather the properties of that system at each of those moments: mass, velocity, rotational radius, height above the ground, and so on, any quantities you can measure to your heart's content. Combine all these numbers by adding, subtracting, multiplying, or dividing them in some way until the result on one side matches the other. Congratulations, you have found a quantity that has not changed, that has been conserved throughout the motion. For example, if a billiard ball collides with a larger ball, you can observe that if you multiply the mass of one ball by its velocity and add the same multiplication for the other ball, you get a number that remains constant throughout the trajectory. This number is called linear momentum, and the fact that it remains constant is known as the conservation of momentum. Similarly, if you analyze the system in which the Earth orbits the Sun, you can verify that if you multiply the mass of the Earth by its distance from the Sun and its velocity at that moment, you obtain another number that does not change at any point in the orbit. This number is called angular momentum, and the fact that it remains constant is known as the conservation of angular momentum. Lastly, if you drop a melon from the fourth floor, you can also confirm that there is a certain combination of its properties that does not change during its fall. This mixture of quantities is what physicists call the total energy of the melon. This expression can be surgically divided into two types of energy that I have already discussed in this video. But essentially, when physicists talk about the energy of an object, they are referring to the sum of these two energies. And surprise, the fact that it remains constant is called the conservation of energy. It is precisely this conservation that gives the sensation that these quantities are like a fluid. For example, since the total amount of momentum cannot change, one part of the system loses it while another part gains it, as if that quantity had been transferred or transformed and could not be created or destroyed. In conclusion, what is energy? If you ask me, it is this compilation of numbers, no auras, no fluids. It is not something you can perceive with your senses in a laboratory. Rather, it is something you can only experience through what is written on a chalkboard. However, the story doesn't end here, because one might ask, why are these quantities conserved? Why do some of them hold true in one case, but not in another? What sets them apart? This was probably the same question that mathematician Noether asked herself during her foray into theoretical physics. With the powerful first Noether's theorem, she showed us how each of these conservations is a manifestation of something deeper: symmetries. Let's think about the Earth orbiting in this system. There is only one interaction at play: the force of gravity. Its intensity depends solely on how close the Earth is to the Sun. If it's very close, the force is strong, and if it's far, it's weaker. However, it doesn't depend on the Earth's position around the Sun. The Sun's gravitational attraction doesn't change if I rotate the Earth by 30, 90, or a couple hundred degrees, because they all share the same proximity to the Sun, which is what modifies the force. In other words, the force of gravity is invariant under rotations. It has rotational symmetry. But beware, this symmetry is not in the system itself. The elliptical orbits don't remain the same once you rotate them. The symmetry lies in the interactions, in the very precursors of motion. Noether demonstrated that these symmetries are reflected through mathematics, causing certain combinations of numbers to remain constant over time: conservation. And once again, this brings us back to what energy is. Energy is that quantity that is conserved when the interactions of a system harbor a symmetry over time. The falling melon is also subject only to the force of gravity, and this force doesn't change with time. The intensity with which the ground pushes you in a certain place is the same as it was 100 or 200 years ago. It hasn't changed. If I perform temporal translations on the force of gravity, like these, it remains the same, invariant. Therefore, it exhibits temporal symmetry, and the quantity that is conserved is energy. But this conservation goes even deeper, because the interactions that do change over time and could break the conservation of energy do not exist. We know that all the forces and interactions we observe can ultimately be reduced to fundamental interactions, and none of them change over time. This is not a coincidence. It corresponds to something more fundamental: the symmetries of spacetime in which these interactions occur. We know that the interactions and the way a physical system moves do not change when I translate the system in space, oriented in a different direction, or activate it at another moment in time. These are spatial, angular, and temporal invariances, and it is from these symmetries that the conservation of linear momentum angular momentum, and energy emerge. The remarkable thing is that these conservations do not depend on the nature of the physical system. They are intrinsic to the spacetime in which we live. So, what is energy? It is a property of spacetime that manifests its temporal homogeneity. When spacetime curves, some symmetries tend to be lost, which can make some of these quantities lose their meaning. And don't get me started on what happens in the quantum world. That's all for today's video. If you liked it, remember that you can subscribe.